Dark matter is a fascinating and mysterious component of our universe, making up about 27% of its total mass and energy. Unlike ordinary matter, which includes stars, planets, and even us, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. The existence of dark matter was first suggested in the early 20th century, when astronomers noticed that galaxies were rotating at speeds that couldn't be explained solely by the visible matter they contained. If we consider the Milky Way, for example, the stars at its outer edges are moving much faster than they should, based on the gravitational pull of the stars and gas we can see. This led scientists to conclude that there must be something else, something unseen, exerting additional gravitational force, and this unseen component was named dark matter. Various experiments and observations have provided indirect evidence for dark matter, such as the behavior of galaxy clusters, which seem to include more mass than what can be accounted for through visible matter alone. The gravitational lensing effect, where light from distant objects is bent around massive objects like galaxy clusters, also suggests the presence of additional mass, further supporting the dark matter hypothesis. Despite being such a critical part of the cosmos, the exact nature of dark matter remains elusive. Many scientists believe that dark matter consists of exotic particles that we haven't yet discovered, such as weakly interacting massive particles, or WIMPs, which are predicted by certain theories in particle physics. There are ongoing efforts around the world to detect these particles, including experiments deep underground, where cosmic rays are less likely to interfere, and through powerful particle accelerators like the Large Hadron Collider. Researchers are also exploring alternative theories that challenge the need for dark matter, such as modifications to our understanding of gravity itself, but these theories have yet to gain widespread acceptance. The quest to understand dark matter not only shapes our understanding of the universe, but also raises profound questions about the very fabric of reality, pushing the boundaries of modern physics. It's a captivating subject that ties together astrophysics, cosmology, and particle physics, demonstrating how much we still have to learn about the universe we inhabit. Dark energy is a fascinating and mysterious force that makes up about 70% of the universe, yet remains largely unknown to scientists. It's not something that we can see or touch, and it doesn't emit light or energy, which is why it's called dark. The concept of dark energy emerged in the late 20th century, particularly after astronomers observed that the universe is not only expanding, but that this expansion is actually accelerating. This was a surprising discovery, as many scientists had assumed that gravity would slow down the expansion over time. Instead, what they found was that galaxies are moving away from us at increasingly faster speeds, suggesting that some unseen force is pushing them apart. The leading explanation for this phenomenon is dark energy, which is thought to have a repulsive effect, counteracting the attractive force of gravity. One of the key theories about dark energy is that it may be related to the vacuum of space itself, which is not empty, but is filled with fluctuating energy fields. This energy density, sometimes referred to as the cosmological constant, could be responsible for the acceleration of the universe's expansion. However, despite extensive research, the exact nature of dark energy remains elusive, and it is one of the biggest mysteries in cosmology today. Scientists are working on various approaches to better understand dark energy, including observations of distant supernovae, cosmic microwave background radiation, and galaxy surveys, all of which could provide clues about its properties. Interestingly, while dark energy is a major component of our universe, it does not seem to affect the behavior of objects on smaller scales, such as within galaxies or solar systems. This means that while it plays a significant role in the large-scale structure of the universe, it doesn't impact our everyday lives in any noticeable way. The quest to understand dark energy is not just about grasping a fundamental aspect of the universe, but it could also lead to deeper insights into the nature of matter, energy, and the fundamental forces that govern our reality. As researchers continue to explore this enigmatic force, They are hopeful that new discoveries will shed light on questions that have puzzled humanity for centuries, and perhaps even redefine our understanding of the cosmos itself. Dark matter was first hypothesized in the early 20th century, when astronomers began to notice some peculiarities in the way galaxies behaved, particularly in terms of their rotation. One of the key figures in this discovery was Fritz Zwicky, a Swiss astronomer, who, in 1933, studied the Coma cluster of galaxies. He observed that the galaxies within this cluster were moving much faster than expected, based on the amount of visible matter, such as stars and gas, present in the cluster. Zwicky applied the concepts of gravitational dynamics and realized that, if the visible mass alone were considered, the galaxies should not be able to hold together. They should be flying apart due to their high speeds. To explain this discrepancy, he proposed the existence of a significant amount of unseen mass, which he called dark matter, that exerted gravitational forces but did not emit light or other forms of electromagnetic radiation, making it invisible and undetectable by conventional means. This idea was further supported by the work of other scientists in the following decades. For instance, in the 1970s, Vera Rubin, an American astronomer, studied the rotation curves of spiral galaxies. She found that the stars at the outer edges of these galaxies were moving at speeds that suggested there was much more mass present than could be accounted for by the visible stars and gas. Rubin's observations reinforced the concept of dark matter, as the gravitational pull required to keep the galaxies intact could only be explained by hypothesizing the presence of this mysterious matter. As research continued into the late 20th and early 21st centuries, further evidence for dark matter accumulated, from the behavior of galaxy clusters to the cosmic microwave background radiation, which provided insights into the early universe's structure. Scientists employed advanced techniques such as gravitational lensing, where light from distant objects is bent around massive objects, allowing researchers to infer the presence of unseen mass. This led to the conclusion that dark matter constitutes about 27% of the universe, while ordinary matter makes up only about 5%. Despite its prevalence, dark matter remains elusive. It does not interact with electromagnetic forces, which is why it does not emit or absorb light, making it difficult to detect directly. Various candidates have been proposed for what dark matter might be, from weakly interacting massive particles, or WIMPs, to axions, but as of now, its true nature remains one of the biggest mysteries in modern astrophysics. Dark matter, a mysterious substance that makes up about 27% of the universe, is a topic of great interest and debate among scientists. While it cannot be seen directly, there is a wealth of evidence that suggests its existence. One of the key pieces of evidence comes from observing the rotation curves of galaxies. When astronomers measure how fast stars orbit the center of their galaxies, they find that the outer stars move much faster than expected based on the visible matter alone. This discrepancy indicates that there is additional unseen mass, which we attribute to dark matter, exerting gravitational influence. Another significant piece of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant galaxies passes near massive objects, like galaxy clusters, it bends, creating a lensing effect. By measuring the amount of bending, astronomers can infer the mass of the foreground object, which often shows that there is much more mass present than what we can see. This extra mass is thought to be dark matter. Cosmic microwave background radiation also provides crucial evidence for dark matter. This faint afterglow of the Big Bang contains a wealth of information about the early universe. Scientists analyze the temperature fluctuations in this radiation, and these fluctuations can be linked to the distribution of both normal and dark matter. The patterns observed match predictions made by models that include dark matter, supporting its existence. Additionally, simulations of large-scale structure formation in the universe, which show how galaxies and galaxy clusters form and evolve, require dark matter to match observations. Without dark matter, the structures we see today would not have formed in the time available since the Big Bang. These simulations can accurately replicate the distribution of galaxies observed in the universe, providing further support for the dark matter hypothesis. Lastly, studies of galaxy clusters, the largest gravitationally bound structures in the universe, also reveal the presence of dark matter. By measuring the temperature of hot gas within these clusters, as well as the motion of the galaxies within them, astronomers can determine the total mass of the cluster. Often, the mass calculated from visible matter alone is far less than the mass inferred from gravitational effects, leading to the conclusion that dark matter must be present. In summary, while we cannot see dark matter directly, the evidence supporting its existence comes from various astronomical observations and theoretical models. These include the rotation curves of galaxies, gravitational lensing, cosmic microwave background radiation, simulations of large-scale structure, and studies of galaxy clusters. Each piece, dark matter, a mysterious substance that makes up about 27% of the universe, remains one of the biggest puzzles in astrophysics. Scientists have proposed several candidates for what dark matter particles could be, some of which are quite intriguing and complex. One of the leading candidates is weakly interacting massive particles, commonly known as WIMPs. These particles are thought to have masses in the range of a few GeV to several hundred GeV, and they interact through the weak nuclear force, which makes them difficult to detect, as they rarely interact with normal matter. Researchers are conducting experiments deep underground in an attempt to catch these elusive particles as they pass through Earth without leaving a trace. Another candidate is axions, which are hypothetical particles that were initially proposed to solve a problem in quantum chromodynamics, a theory that describes the strong force. Axions are expected to have very low masses and would interact very weakly with ordinary matter. Much like WIMPs, they could also be produced in the early universe, and there are experiments underway, like the axion dark matter experiment, aimed at detecting them through their faint interactions with electromagnetic fields. Then, there are sterile neutrinos, a type of neutrino that does not interact through the weak force, making them even harder to detect. These particles are thought to be heavier than regular neutrinos, and they could explain certain anomalies observed in neutrino experiments. Their existence could also help in understanding the formation of large-scale structures in the universe, as they could play a role in the early moments after the Big Bang. In addition, primordial black holes, which are black holes formed soon after the Big Bang, have gained attention as potential dark matter candidates. They could account for dark matter if they exist in the right mass range, although their existence is still a matter of debate among scientists. Finally, there are theories involving modified gravity rather than new particles. Some scientists propose that dark matter effects could be explained by changing the laws of gravity rather than positing the existence of new particles. This approach, while not as widely accepted, opens up new avenues for understanding the universe's behavior without needing dark matter. These candidates, from WIMPs to axions, sterile neutrinos, primordial black holes, and modified gravity theories, illustrate the rich landscape of research surrounding dark matter. Each has its own set of challenges and opportunities for discovery, and as technologies improve, we may soon uncover the true nature of this. Dark matter plays a crucial role in the formation of galaxies, acting as an invisible scaffold that shapes the universe, even though we cannot see it directly. It is believed that dark matter makes up about 27% of the universe, while ordinary matter, which forms stars, planets, and living things, accounts for only about 5%. The remaining percentage is made up of dark energy. When the universe was young, shortly after the Big Bang, it was filled with hot gas and radiation, and as it expanded, it began to cool down. As the matter in the universe started to clump together due to gravity, dark matter, which interacts through gravity but not through other forces, began to influence this process significantly. The gravitational pull of dark matter allowed regions of ordinary matter to collapse and form the very first stars and galaxies. Think of dark matter as a sort of cosmic glue, helping to hold galaxy clusters together, while the ordinary matter, which we can see, falls into the gravitational wells created by dark matter. This process is not immediate. It takes billions of years for galaxies to form and evolve, but dark matter sets the stage for this evolution. As galaxies formed, dark matter halos, which are large spherical regions filled with dark matter, surrounded them. These halos are thought to be much larger than the galaxies themselves, containing more mass than the visible components of the galaxies. The gravitational effects of these halos are so strong that they can influence the motion of stars within galaxies and even the paths of galaxies as they move through space. This interaction between dark matter and ordinary matter is essential for understanding the structure and behavior of galaxies. Moreover, dark matter affects the way galaxies cluster together. In regions where there is a lot of dark matter, galaxies tend to group more tightly, while in areas with less dark matter, galaxies are more spread out. This clustering is observed in the large-scale structure of the universe, where galaxies are found in filaments and voids, indicating the underlying influence of dark matter. Additionally, simulations of galaxy formation that include dark matter provide insights into how galaxies look today. These simulations show that without dark matter, galaxies would not have formed in the same way, leading to a universe that is very different from the one we observe. The presence of dark matter helps explain why we see more spiral galaxies, elliptical galaxies, and irregular galaxies than we would expect if only regular matter were at play. In summary, dark matter is fundamental in shaping the universe. Dark matter plays a crucial, yet often mysterious, role in the cosmic microwave background radiation, which is the faint glow left over from the Big Bang, filling the universe almost uniformly. This radiation, discovered in 1965, provides a snapshot of the universe when it was just about 380,000 years old, allowing scientists to glean important information about its early structure and composition. Dark matter, which does not emit, absorb, or reflect light, constitutes a significant portion of the universe's total mass and is essential in influencing the formation and distribution of matter in the cosmos. As the universe expanded and cooled after the Big Bang, the density fluctuations in matter led to the uneven distribution of galaxies and galaxy clusters we observe today. Dark matter, due to its gravitational effects, help to amplify these density fluctuations. Although dark matter cannot be directly observed, its presence is inferred from the gravitational effects it has on visible matter, radiation, and the large-scale structure of the universe. In the context of the cosmic microwave background, dark matter affects the way light from the early universe interacts with matter. The gravitational influence of dark matter helped to shape the potential wells in which normal matter could fall into, leading to the formation of the first stars and galaxies. This gravitational influence also led to the slight irregularities seen in the cosmic microwave background, which are crucial for understanding the evolution of the universe. These irregularities, or anisotropies, in the temperature of the cosmic microwave background, reflect the density variations of matter at that early stage. The study of these anisotropies has provided valuable clues about the amount of dark matter in the universe, as well as its properties. For instance, measurements from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have helped scientists refine their understanding of dark matter's role in cosmic evolution. The patterns in the cosmic microwave background also suggest that dark matter is likely cold, meaning it moves slowly compared to the speed of light, allowing it to clump together and form the large-scale structure we observe today. Furthermore, dark matter is thought to account for about 27% of the universe's total energy density, dominating over the ordinary matter, which makes up only about 5%. This stark contrast shapes the universe's geometry and fate. The interplay between dark matter and the cosmic microwave background is a key focus for astrophysicists, as it helps bridge our understanding of the early universe with the structure we see in the present day. Dark energy plays a crucial role in the expansion of the universe, acting as a mysterious force that drives it to stretch and grow at an accelerating rate. To understand this, we first need to acknowledge that the universe has been expanding since the Big Bang, which occurred around 13.8 billion years ago. Initially, this expansion was slowing down due to the gravitational pull of matter, both ordinary and dark matter. However, observations made in the late 1990s, particularly those involving distant supernovae, revealed a surprising twist. The universe's expansion is not just continuing, but is actually speeding up. This unexpected acceleration led scientists to propose the existence of dark energy, which is estimated to make up about 68% of the total energy content of the universe. But what exactly is dark energy? While it remains one of the greatest mysteries in cosmology, dark energy is generally thought to act like a sort of anti-gravity force, countering the attractive pull of gravity from matter. This means that, as the universe expands, dark energy becomes more influential, pushing galaxies apart at an increasing rate. One of the leading theories is that dark energy is related to the concept of vacuum energy, which arises from the empty space itself, suggesting that even in a vacuum, there is energy present that contributes to the expansion of the universe. Additionally, the equations of general relativity, formulated by Albert Einstein, describe how matter and energy interact with the fabric of space-time. When applying these equations to the universe, scientists find that the presence of dark energy leads to a dynamic model where the rate of expansion can change over time. The cosmological constant, introduced by Einstein himself, is one way to represent dark energy mathematically, as it adds a uniform energy density to space that does not change as the universe expands. The implications of dark energy are profound, affecting not just the fate of the universe, but also our understanding of fundamental physics. For instance, if dark energy remains constant, the universe could continue expanding forever, eventually leading to a scenario known as the Big Freeze, where galaxies drift apart beyond the reach of each other, resulting in a cold and dark cosmos. Alternatively, if dark energy changes over time, the future could unfold differently, potentially leading to a big crunch or even other exotic outcomes. In recent years, scientists have been studying the effects of dark energy through various means, including analyzing the cosmic microwave background radiation and mapping the distribution of galaxies across the universe. The discovery of cosmic acceleration, which refers to the observation that the universe is expanding at an increasing rate, holds profound significance for our understanding of the cosmos. This phenomenon was first identified in the late 1990s through observations of distant supernovae, which revealed that these stellar explosions were dimmer than expected, indicating that they were farther away than previously thought. This unexpected result led scientists to conclude that something was driving this accelerated expansion, a force that was later dubbed dark energy. Dark energy is thought to make up about 70% of the universe, yet its exact nature remains one of the greatest mysteries in modern astrophysics. The significance of cosmic acceleration extends beyond just the expansion itself. It challenges our fundamental understanding of gravity, the fabric of space-time, and the fate of the universe. The implications are vast, as they suggest that the universe may not only be expanding, but could also be heading towards a future where galaxies drift apart, leading to a cold, dark cosmos known as the Big Freeze. This discovery has also prompted a plethora of research into alternative theories, such as modifications to Einstein's general relativity or the existence of additional dimensions. Scientists are actively exploring various hypotheses to explain dark energy, from quantum fluctuations in empty space to the possibility of a cosmological constant, which Einstein originally introduced but later discarded. The significance of cosmic acceleration also resonates in the field of cosmology, where it has spurred advancements in observational techniques and technologies, leading to improved telescopes and instruments that can probe deeper into space and time. The accelerating universe challenges our philosophical views about the nature of reality and our place within it, as it suggests that the universe is dynamic and ever-changing, rather than static and eternal. The fact that we live in a time where we can observe such phenomena opens up exciting possibilities for future discoveries. As scientists continue to unravel the complexities of dark energy and its role in the evolution of the cosmos, understanding cosmic acceleration not only enriches our knowledge of the universe, but also feeds our curiosity about fundamental questions, such as why the universe is structured the way it is, and what the ultimate fate of everything we know might be. This ongoing quest for knowledge keeps astronomers and physicists engaged as they strive to piece together the puzzle of dark energy and cosmic acceleration, which could redefine our grasp of the universe itself and perhaps even lead to breakthroughs in our understanding of the laws of physics. In the vast landscape of cosmology, dark matter and dark energy play pivotal roles, yet they represent two distinct components of the universe, each contributing uniquely to its overall structure and evolution. Dark matter, which accounts for about 27% of the universe's total mass and energy content, is thought to be composed of particles that do not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. On the other hand, dark energy, which constitutes approximately 68% of the universe, is a mysterious force driving the accelerated expansion of the cosmos, acting in opposition to the attractive force of gravity. In cosmological models, dark matter and dark energy are interrelated in that they both influence the dynamics of the universe, but they do so in different ways. While dark matter clusters under the influence of gravity, forming galaxies and large-scale structures, dark energy works to counteract this clustering, promoting an accelerated expansion. This duality creates a complex interplay that is crucial for understanding the evolution of the universe. For instance, in the widely accepted lambda-cold dark matter model, often referred to as LCDM, dark energy is represented by the cosmological constant lambda, a term introduced by Albert Einstein, which accounts for the energy density of empty space, while cold dark matter refers to the type of dark matter that moves slowly compared to the speed of light, allowing it to clump together under gravity. As researchers study the cosmic microwave background radiation, galaxy formation, and large-scale structure, they find that the presence of dark matter is essential for the formation of galaxies, while dark energy affects the rate at which these galaxies move apart from each other. The relationship between dark matter and dark energy is also a significant focus of ongoing research, as scientists seek to understand how these components interact over cosmic time. In some models, the evolution of dark energy might change, influencing the behavior of dark matter and the future of the universe. The implications of their relationship extend to cosmological observations, including supernovae studies and galaxy redshift surveys, which provide insights into how the universe has expanded and evolved over billions of years. By analyzing these observations, cosmologists can refine their understanding of dark matter and dark energy, revealing more about their properties and how they shape the cosmos. The interplay between these two mysterious entities raises profound questions about the fundamental nature of reality and the ultimate fate of the universe, challenging our understanding and inspiring further exploration into the unknown. In the quest to understand dark matter, scientists are employing a variety of innovative experimental methods, each designed to uncover the elusive nature of this mysterious substance. One prominent approach involves the use of direct detection experiments, which aim to observe dark matter particles interacting with normal matter. These experiments typically take place deep underground, in locations like the Gran Sasso Laboratory in Italy or the Sanford Underground Research Facility in South Dakota, where cosmic rays and other background noise can be minimized. Detectors, often made from materials like xenon or germanium, are cooled to very low temperatures to increase sensitivity, and they rely on extremely precise measurement techniques to catch even the faintest signals that might indicate a dark matter interaction. Another method, known as indirect detection, seeks to identify the products of dark matter annihilation or decay. This approach often utilizes telescopes and observatories, such as the Fermi Gamma Ray Space Telescope or the IceCube Neutrino Observatory, looking for high-energy particles like gamma rays, neutrinos, or antimatter that could be produced when dark matter particles collide and annihilate each other. These observatories analyze vast amounts of data from the cosmos, searching for anomalies that could indicate the presence of dark matter. Particle accelerators, such as the Large Hadron Collider at CERN, are also pivotal in the search for dark matter. By smashing protons together at incredibly high energies, scientists hope to create conditions where dark matter particles can be produced. They analyze the resulting collisions, looking for missing energy and momentum that could suggest the presence of undetected particles, potentially leading to new physics beyond the standard model. Additionally, astrophysical observations provide crucial data about dark matter. For instance, studying the rotation curves of galaxies, scientists have found that stars at the edges of galaxies rotate faster than expected, suggesting that there is more mass present than what we can see. This has led to the development of various simulation models that incorporate dark matter to better understand the structure and formation of galaxies. Moreover, some researchers are exploring the concept of self-interacting dark matter, which posits that dark matter particles might interact with each other in ways that could be detectable through their gravitational effects on galaxies and galaxy clusters. Experiments are designed to test these theories, providing new insights into how dark matter influences the universe. In the realm of theoretical physics, scientists are also considering various dark matter candidates, such as weakly interacting massive particles, or WIMPs, and axions, leading to tailored experimental designs that gravitational lensing, a fascinating phenomenon where massive objects, like galaxies or clusters of galaxies, bend the light from more distant objects, offers compelling evidence for the existence of dark matter, which is an elusive and mysterious substance thought to make up a significant portion of the universe's mass. When light from a background galaxy passes near a foreground massive object, the gravitational field of that object distorts the path of the light, creating a lensing effect that can magnify, distort, or multiply the images of the distant galaxy. This effect is not merely an optical illusion. It provides astronomers with powerful tools to study the distribution and amount of mass in the universe. The key to understanding how this supports dark matter theories lies in the discrepancy between the visible matter we can observe and the gravitational effects we measure. For instance, when observing a galaxy cluster, astronomers can calculate how much mass is present by observing the lensing effect on background galaxies. The observed lensing often reveals far more mass than what can be accounted for by the visible matter, such as stars and gas. This discrepancy strongly suggests that there is additional mass which does not emit light, hence the term dark matter. Moreover, gravitational lensing is not only useful in galaxy clusters, but also on smaller scales. For example, studies of individual galaxies using gravitational lensing have shown that there is a significant amount of mass extending beyond the visible edges of galaxies, which aligns with predictions made by dark matter theories. The distribution of the lensing effects provides clues about how dark matter might be spread out in a halo around galaxies, influencing their formation and dynamics. Additionally, the cosmic microwave background radiation, which is the afterglow of the Big Bang, also shows patterns that indicate how matter, including dark matter, is distributed across the universe. The way the gravitational lensing affects this radiation supports models of dark matter, as the fluctuations observed are consistent with simulations that include dark matter's effects. In essence, gravitational lensing serves as a critical observational tool that not only reinforces the existence of dark matter, but also helps researchers map its distribution throughout the universe, revealing the intricate web of cosmic structure that we see today. This research continues to evolve, with advancements in observational technology allowing for more precise measurements, further illuminating the role of dark matter in the grand tapestry of the cosmos. Baryonic and non-baryonic dark matter are two important concepts in astrophysics, particularly when discussing the composition of the universe. Baryonic dark matter refers to matter made up of baryons, which are particles such as protons and neutrons that make up ordinary matter, like stars, planets, and even our own bodies. This type of dark matter includes objects that emit, absorb, or reflect light, albeit in ways that are often difficult to detect, such as black holes, neutron stars, or even faintly glowing gas clouds. While baryonic matter is a significant part of the universe, it only makes up a small fraction of the total mass energy content. On the other hand, non-baryonic dark matter encompasses a variety of hypothetical particles that do not interact with electromagnetic forces, meaning they do not emit, absorb, or reflect light, making them invisible and detectable only through their gravitational effects. The most widely discussed candidate for non-baryonic dark matter is a type of particle called WIMPs, or weakly interacting massive particles, which are thought to be abundant in the universe and could help explain the formation of galaxies and the large-scale structure of the cosmos. Another candidate includes axions, which are lighter and even more elusive than WIMPs. The distinction between these two types of dark matter is crucial for understanding how the universe evolved. Baryonic dark matter is generally found in the more visible structures of the universe, while non-baryonic dark matter is believed to be more widespread, influencing the motion of galaxies and galaxy clusters and playing a key role in the universe's overall gravitational framework. The search for non-baryonic dark matter is ongoing, with scientists conducting various experiments to detect these elusive particles, hoping to uncover their properties and understand their role in the cosmos. In summary, while baryonic dark matter is related to the matter we can see and interact with, non-baryonic dark matter remains a mystery, hidden from direct observation, yet profoundly impacting the universe's structure and dynamics. The ongoing research into these two types of dark matter continues to be a key area of study in cosmology, as it has the potential to reshape our understanding of the universe itself. Simulations play a crucial role in our understanding of dark matter, which, despite making up about 27% of the universe, remains one of the most mysterious components of our cosmos. By creating computer models that mimic the behavior of galaxies and large-scale structures, scientists can explore how dark matter influences the formation and evolution of the universe. These simulations take into account the laws of physics, particularly gravity, and incorporate the known behaviors of visible matter, allowing researchers to visualize how dark matter interacts with regular matter over billions of years. Through these simulations, scientists can investigate various scenarios, such as how dark matter clumps together, forming halos around galaxies, and how it affects the motion of stars and galaxies. This is important because the gravitational effects of dark matter can be observed indirectly through the movement of visible matter. For instance, galaxies rotate at speeds that suggest there is much more mass present than what we can see. Simulations help us understand why galaxies spin the way they do, providing insights into the distribution of dark matter in and around these cosmic structures. Moreover, simulations allow researchers to test different theories about the nature of dark matter, including whether it consists of weakly interacting massive particles, or WIMPs, or if it could be something entirely different, like axions or other exotic particles. By comparing the output of simulations with observational data, scientists can refine their models and gain a clearer picture of how dark matter impacts the universe on both large and small scales. Additionally, these simulations can predict phenomena that we might not have observed yet, guiding astronomers to look for specific signatures of dark matter in the universe. For example, they can simulate the cosmic microwave background radiation and predict how dark matter would affect its temperature fluctuations, providing a tool to study the early universe and the conditions that led to the formation of galaxies. In essence, simulations are like virtual laboratories where scientists can experiment with the universe's ingredients, testing hypotheses about dark matter's role and behavior without needing to directly observe it. They help bridge the gap between theory and observation, leading to a deeper understanding of not just dark matter, but the fundamental workings of the universe itself. Dark energy, a mysterious force that makes up about 68% of the universe, plays a critical role in determining its fate. Discovered in the late 1990s, Through observations of distant supernovae, dark energy is believed to be responsible for the accelerated expansion of the universe. This expansion suggests that, rather than slowing down due to gravity, the universe is actually stretching faster and faster, which raises intriguing questions about its long-term destiny. The impact of dark energy is profound, as it influences the rate at which galaxies move apart from each other. If the influence of dark energy continues to dominate, the universe may face a future known as the Big Freeze. In this scenario, galaxies will drift away from one another, stars will burn out, and the universe will become increasingly cold and dark, leading to a state of near absolute emptiness where no new stars are formed. Conversely, if dark energy were to weaken over time, the gravitational forces of matter could eventually take over, leading to a deceleration of the expansion. This could result in a big crunch, where the universe might collapse back into a singular point. However, current observations suggest that dark energy is constant, which means the big crunch is less likely to happen. Some scientists also propose that dark energy could change in intensity, which might lead to other fates for the universe. For instance, if dark energy were to increase dramatically, it could lead to a scenario called the Big Rip, where galaxies, stars, planets, and eventually atoms would be torn apart as the expansion becomes too strong to hold them together. This illustrates how dark energy not only shapes the current dynamics of the universe, but also poses fundamental questions about its ultimate fate. The discovery of dark energy has sparked a wealth of research, and scientists are exploring its nature through various means, including observations of cosmic microwave background radiation and large-scale structure surveys. These studies are crucial for understanding not only dark energy but also the overall composition of the universe. As researchers delve deeper into the mysteries of dark energy, they hope to unlock the secrets of the cosmos, revealing how this enigmatic force will dictate the future of everything we see around us. Dark matter, a mysterious and invisible substance, plays a crucial role in shaping the structure of the universe, particularly in what we call the cosmic web. This cosmic web is a vast network of galaxies, clusters, and filaments, forming a complex structure that spans the universe. To understand the significance of dark matter in this context, we must first recognize that it makes up about 27% of the universe's total mass energy content, while ordinary matter, which includes stars, planets, and all visible objects, accounts for only about 5%. The rest is dark energy, which is responsible for the accelerated expansion of the universe. In the early universe, shortly after the Big Bang, dark matter began to influence the formation of cosmic structures. Unlike ordinary matter, which interacts through electromagnetic forces and can radiate light, dark matter interacts primarily through gravity. This means that while we cannot see dark matter directly, we can observe its effects on visible matter. As the universe expanded and cooled, slight density fluctuations in the dark matter began to gravitationally attract surrounding gas and dust, leading to the formation of the first structures. As these structures grew, dark matter acted like a scaffold, providing the gravitational pull necessary for ordinary matter to clump together. Over billions of years, these clumps evolved into galaxies, galaxy clusters, and superclusters, all interconnected by vast filaments of dark matter. These filaments act as highways for galaxies, guiding them along the cosmic web. Observations of large-scale structures in the universe, such as the Sloan Digital Sky Survey, reveal that galaxies are not evenly distributed. Instead, they are found along these filaments, with vast voids in between. Furthermore, dark matter influences the dynamics of galaxies themselves. The rotation curves of galaxies, which depict how fast stars are moving at various distances from the center, show that stars far from the galactic center are moving much faster than expected based on the mass we can see. This discrepancy indicates the presence of a significant amount of unseen mass, attributed to dark matter, which is distributed in a halo around galaxies. This halo extends far beyond the visible parts of galaxies, further illustrating the importance of dark matter in the cosmic structure. Additionally, simulations of the universe's evolution, which factor in dark matter, align closely with the distribution of galaxies we observe today. These simulations show how dark matter facilitates the merging of smaller structures into larger ones, creating the complex web we see. Without dark matter, the universe would look vastly different. Mapping dark matter in the universe is a fascinating and complex endeavor, primarily because dark matter does not emit, absorb, or reflect light, making it invisible and difficult to detect directly. Instead, astronomers and physicists rely on its gravitational effects to infer its presence and distribution. One of the primary methods used to map dark matter is gravitational lensing, which occurs when massive objects, such as galaxy clusters, bend the light from more distant galaxies. This bending effect allows scientists to create maps of dark matter by analyzing how much light is being distorted, revealing not only the location of dark matter, but also its density. When researchers study the way light is warped around these massive objects, they can estimate the mass of the dark matter that is present, as the degree of bending correlates with the mass of the lensing object. Another technique for mapping dark matter involves the study of galaxy rotation curves. In a galaxy, the stars and gas rotate around the center, and by measuring their speeds, scientists can determine how much mass is present. Surprisingly, observations show that the outer stars in galaxies rotate at much higher speeds than would be expected from the visible matter alone. This discrepancy suggests the existence of a substantial amount of unseen mass, which is attributed to dark matter, extending beyond the visible edges of galaxies. Cosmic microwave background, or CMB, observations also provide crucial data about dark matter. The CMB is the afterglow radiation from the Big Bang, and tiny fluctuations in this radiation can reveal information about the early universe's matter content. By analyzing these fluctuations, scientists can infer the distribution of dark matter throughout the universe's history, helping to create a large-scale map of dark matter's influence on cosmic structure. Additionally, simulations and computer models play a vital role in mapping dark matter. Researchers use these models to simulate the universe's formation and evolution, taking into account the gravitational effects of both visible matter and dark matter. By comparing these simulations with actual observations, scientists can refine their understanding of dark matter's distribution and its role in shaping galaxies and galaxy clusters. Lastly, large-scale surveys and projects, such as the Sloan Digital Sky Survey and the Dark Energy Survey, contribute to mapping dark matter by providing extensive data on galaxy positions, shapes, and distributions. These surveys help scientists understand how dark matter influences the structure of the universe on a grand scale, leading to a better understanding of its properties and behavior. Collectively, these methods allow astronomers to piece together a comprehensive picture of dark matter. Dark energy, an enigmatic force that makes up about 70% of the universe, plays a crucial role in our understanding of cosmology, particularly in relation to the Big Bang Theory. Its implications are profound, as it challenges and enhances our comprehension of the universe's expansion. The Big Bang Theory posits that the universe began as an incredibly hot, dense point and has been expanding ever since. Initially, this expansion was thought to be slowing down due to the gravitational attraction of matter. However, observations in the late 90s, particularly those involving distant supernovae, revealed a surprising twist. The expansion of the universe is actually accelerating, not slowing down. This led to the hypothesis of dark energy, which acts as a sort of anti-gravity, pushing galaxies apart. One of the major implications of dark energy is that it suggests the universe's fate is not what we once thought. If the expansion continues to accelerate, the universe could eventually evolve into a big freeze, where galaxies drift apart, stars burn out, and the cosmos becomes a cold, dark place. This scenario differs significantly from earlier models, which considered possibilities like a big crunch, where the universe might eventually collapse back into a singularity due to gravitational forces. Dark energy implies a universe that is not just expanding, but doing so at an ever-increasing rate, which profoundly alters our predictions about its ultimate fate. Moreover, dark energy raises questions about the nature of the cosmos itself. It suggests that the majority of the universe's energy content is invisible and undetectable directly, leading to theories that challenge our understanding of physics. Some scientists hypothesize that dark energy could be linked to a property of space itself, while others consider it might be a sign that our understanding of gravity, or even Einstein's theory of general relativity, may need to be revised at cosmic scales. This has sparked a flurry of research and experimentation as physicists seek to understand the fundamental forces at play. The presence of dark energy also impacts the formation and distribution of cosmic structures. As the universe expands, the influence of dark energy becomes more dominant, affecting the way galaxies cluster and evolve over time. This has implications for our understanding of galaxy formation, as well as the distribution of dark matter, which interacts with both normal matter and dark energy. The interplay between these forces is crucial for developing accurate models of the universe's evolution and structure. Finally, dark energy may hold the key to answering some of the most profound questions about supernovae, especially Type Ia supernovae, have played a crucial role in our understanding of dark energy, which is the mysterious force driving the accelerated expansion of the universe. When astronomers first observed Type Ia supernovae in the late 1990s, they were looking for standard candles, objects with a known brightness, to measure distances in the universe. These supernovae occur in binary systems, where one star is a white dwarf that accumulates matter from its companion star until it reaches a critical mass, leading to a catastrophic explosion. The brightness of these explosions is remarkably consistent, allowing astronomers to calculate their distances based on how dim they appear from Earth. By measuring the distance to these supernovae and comparing them to their redshift show fast they are moving away from us, scientists discovered something unexpected. Instead of slowing down as was anticipated due to gravity, the expansion of the universe is actually accelerating. This finding was surprising and led to the conclusion that some form of dark energy must be present, exerting a repulsive force that counteracts gravity on cosmic scales. The observations of supernovae provided strong evidence for this acceleration, suggesting that dark energy makes up about 70% of the universe's total energy density. Researchers have since developed various models to explain dark energy, with the cosmological constant being one of the most widely accepted. This constant represents a fixed energy density filling space homogeneously, but there are alternative theories, such as quintessence, which propose that dark energy could change over time. The connection between supernovae and dark energy is not just theoretical. It has practical implications for understanding the fate of the universe. As scientists continue to observe more supernovae, they refine their measurements and gain insights into the nature of dark energy, its effects on cosmic expansion, and how it influences the large-scale structure of the universe. The ongoing research in this area remains vibrant, as new telescopes and technologies allow for more detailed observations, leading to deeper questions about the fundamental workings of our universe. The cosmological constant is a term that comes from the field of cosmology, which is the study of the universe as a whole. It was first introduced by Albert Einstein in 1917, when he was trying to explain why the universe is static, meaning neither expanding nor contracting. At that time, most scientists believed the universe was unchanging, but Einstein's equations of general relativity suggested that, without some form of additional pressure, the universe should either be collapsing under gravity or expanding. To avoid this, he added what he called a cosmological constant, a kind of energy density that fills space homogeneously. This constant, represented by the Greek letter lambda, is thought to create a repulsive force, counteracting the pull of gravity. For many years, this idea was set aside, especially after Edwin Hubble's discovery in the 1920s that the universe is actually expanding, which seem to make the cosmological constant unnecessary. However, the cosmological constant made a comeback in the late 1990s, when two independent teams of astronomers observed distant supernovae and found that they were dimmer than expected. This surprising result suggested that the expansion of the universe is not just continuing, but accelerating. To explain this acceleration, scientists proposed a form of energy that permeates all of space, which is consistent with what the cosmological constant represents. This energy is now often referred to as dark energy, and it is estimated to make up about 68% of the total energy content of the universe. The cosmological constant, therefore, is a crucial piece in the puzzle of understanding how the universe behaves on the largest scales. In essence, the cosmological constant can be thought of as a measure of the energy density of empty space. It suggests that, even in a vacuum, there is a kind of energy that can have significant effects on the dynamics of the universe, particularly on how quickly it expands. While Einstein originally considered the cosmological constant to be his greatest blunder after the discovery of the expanding universe, it has since become a fundamental aspect of modern cosmological theories, including the widely accepted lambda-cold dark matter model, which describes the overall structure and evolution of the universe. The implications of the cosmological constant are profound, raising questions about the ultimate fate of the universe, the nature of dark energy, and our understanding of physics at the most fundamental level. As research continues, scientists are exploring various theories and experiments to further. Alternative theories to dark matter and dark energy often arise from a desire to explain observations in the universe without invoking these mysterious components which make up most of the cosmos yet remain undetected through traditional means. One prominent alternative is modified Newtonian dynamics, or MOND, which suggests that the laws of gravity change at low accelerations. This theory aims to explain the flat rotation curves of galaxies, which indicate that they rotate at speeds that cannot be accounted for by the visible matter alone. According to MOND, gravity behaves differently under certain conditions, allowing galaxies to hold together without the need for dark matter. Another intriguing approach is the concept of emergent gravity, proposed by physicist Erik Verlinde. This theory posits that gravity is not a fundamental force, but rather an emergent phenomenon arising from the information associated with the positions of matter in space. In this view, what we perceive as dark matter could actually be a result of the way gravity behaves in a universe filled with entropy and information. Additionally, some researchers explore the possibility of modified gravity theories, which suggest that the laws of gravity as we know them, particularly Einstein's general relativity, might not be entirely accurate on cosmic scales. These theories, such as the FR gravity models, aim to modify the equations of gravity to account for the accelerated expansion of the universe without needing dark energy. There are also ideas involving the presence of extra dimensions, where our familiar three-dimensional space might be part of a higher dimensional universe. In such frameworks, the effects we attribute to dark matter and dark energy could arise from the geometry of these extra dimensions, altering how we perceive gravitational interactions. Moreover, the concept of plasma cosmology presents an alternative view, emphasizing the role of electromagnetic forces in shaping the universe rather than relying solely on gravity. Proponents of this theory argue that plasma interactions could explain the large-scale structures and behaviors of celestial bodies without requiring dark matter or dark energy as explanations. These alternative theories challenge the standard model of cosmology by proposing that our understanding of the universe's composition and the fundamental laws of physics may need revision. They invite researchers to reconsider the evidence and observations, encouraging a broader exploration of the universe's mysteries, while also highlighting the importance of questioning established paradigms in the pursuit of scientific knowledge. The relationship between dark matter and galaxy rotation curves is a fascinating topic that has captured the interest of astronomers and physicists alike, as it touches on fundamental aspects of our understanding of the universe. When we observe galaxies, we notice that they rotate, and the speed at which they spin can be measured by looking at the light emitted from stars within them. According to the laws of physics, particularly Newtonian mechanics, we would expect that stars farther from the center of a galaxy, where most of the visible mass is concentrated, should move more slowly than those closer in. However, what we actually observe is quite different. The rotation curves, which plot the rotational speed of stars against their distance from the galaxy's center, tend to remain flat, or even rise slightly, instead of decreasing as one would expect from the visible mass alone. This discrepancy leads to the conclusion that there must be much more mass present in galaxies than we can see, hence the term dark matter, which refers to this unseen mass that does not emit light or energy that we can detect directly. The flat rotation curves imply that the gravitational influence of dark matter extends well beyond the visible components of galaxies, suggesting that dark matter forms a halo around galaxies, influencing their rotation and structure. This dark matter halo is thought to be composed of particles that interact very weakly with ordinary matter, which is why we have not yet been able to detect it directly. The existence of dark matter was first proposed in the 1930s by astronomer Fritz Zwicky, who noticed that the mass of galaxy clusters, inferred from their gravitational binding, was much greater than the mass calculated from the visible galaxies. Subsequent observations of individual galaxies, particularly those conducted by Vera Rubin in the 1970s, provided strong evidence supporting the dark matter hypothesis, as she found that the rotation curves of galaxies did not decline as expected, but instead remained flat at greater distances from the galactic center. This relationship between dark matter and galaxy rotation curves has profound implications for cosmology, as it suggests that dark matter constitutes a significant portion of the total mass-energy content of the universe, influencing the formation and evolution of galaxies. Furthermore, it raises intriguing questions about the nature of dark matter itself. As scientists continue to explore various candidates for what this elusive substance might be, ranging from weakly interacting massive particles, or WIMPs, to more exotic possibilities like axions or sterile neutrinos. Each of these candidates comes with its own set of theoretical. Scientists distinguish between dark matter and normal matter, primarily through their different interactions with light and gravity. Normal matter, which makes up stars, planets, and living beings, interacts with electromagnetic radiation, allowing it to emit, absorb, or reflect light. This property enables astronomers to observe and study normal matter using telescopes across various wavelengths, from radio waves to gamma rays. In contrast, dark matter does not interact with light in any meaningful way, making it invisible and detectable only through its gravitational effects. One of the key methods scientists use to identify dark matter is by observing the rotation curves of galaxies. When astronomers measure the speed at which stars orbit the center of a galaxy, they find that the stars at the edges are moving much faster than what would be expected from the visible matter present. According to Newton's laws, if only normal matter were influencing the stars' motions, the outer stars should be moving slower. However, the faster speed suggests there is additional mass which we cannot see, exerting gravitational influence. This unseen mass is attributed to dark matter. Another technique involves studying gravitational lensing, where the gravity of a massive object bends the light from objects behind it. When scientists observe how light is distorted as it passes near galaxy clusters, they can map the distribution of mass in that cluster, including dark matter. This effect demonstrates that there is much more mass present than what can be accounted for by normal matter alone, further supporting the existence of dark matter. Cosmic microwave background radiation, or CMB, also provides insights into the composition of the universe. This radiation is the afterglow of the Big Bang and carries information about the early universe. By analyzing temperature fluctuations in the CMB, scientists can infer the density of normal and dark matter in the universe, allowing them to estimate the proportion of dark matter compared to regular matter. Furthermore, Computer simulations of cosmic structure formation help scientists understand how galaxies form and evolve under the influence of both normal and dark matter. These simulations can replicate observed structures in the universe only when a significant amount of dark matter is included, as it plays a crucial role in gravitational attraction during the early stages of galaxy formation. Finally, particle physics experiments, such as those conducted at the Large Hadron Collider, aim to directly detect dark matter particles or produce them in controlled conditions. Although no conclusive evidence has yet been found, the search continues, and any discovery would help clarify how dark matter differs from normal matter on a fundamental level. Through these diverse, the concept of dark energy is both fascinating and perplexing, as it represents a significant portion of the universe, yet remains largely mysterious. Dark energy, which is thought to make up about 68% of the universe, is believed to be responsible for the accelerated expansion of the cosmos. This expansion has profound implications for the future of cosmic structures. As the universe continues to expand, galaxies will gradually move away from each other, leading to a phenomenon known as cosmic isolation. In this scenario, distant galaxies will recede beyond our observable horizon, making it impossible for us to see them or for them to interact with us, ultimately leading to a universe that feels increasingly empty. Additionally, the influence of dark energy could alter the fate of galaxy clusters and superclusters. As the expansion accelerates, gravitational forces that once helped to pull these structures together may become insufficient to counteract the effects of dark energy. This could lead to fewer galaxy mergers over time, which means that the large-scale structure of the universe will evolve in a more isolated manner. Over billions of years, galaxy clusters might become more sparse, and smaller galaxies could dominate the cosmic landscape, creating a universe filled with less massive, isolated structures. Moreover, the ultimate fate of the universe, influenced by dark energy, might lead to scenarios such as the Big Freeze. As dark energy continues to drive the acceleration of cosmic expansion, galaxies will drift apart, stars will exhaust their nuclear fuel, and the universe will cool and darken over trillions of years. Eventually, this could result in a lifeless cosmos, where existing stars fade away, leaving a vast expanse of dark space filled with remnants of stars and galaxies that once were. On the other hand, if dark energy's properties change over time, which some theories suggest is possible, this could lead to different outcomes, such as a deceleration of the expansion, or even a reversal that might eventually result in a big crunch, where the universe collapses back into a singularity. However, current observations support the idea that dark energy is consistent and remains a driving force in the universe's expansion. The potential consequences of dark energy are not just confined to the distant future. They also affect our understanding of fundamental physics, cosmology, and the very nature of the universe itself. As scientists continue to explore the properties and implications of dark energy, we may uncover more about how it shapes cosmic structures, influences the behavior of galaxies. The lambda-cold dark matter, often abbreviated as LCDM, is a widely accepted cosmological model that provides a framework for understanding the large-scale structure and evolution of the universe. This model incorporates two key components: lambda L, which represents dark energy, and cold dark matter CDM, which refers to a form of matter that does not emit light or energy, making it invisible and detectable only through its gravitational effects. The LCDM model explains cosmic phenomena by demonstrating how these components interact to shape the universe as we know it. In the early universe, shortly after the Big Bang, the LCDM model suggests that the universe was extremely hot and dense, filled with a nearly uniform mixture of particles, radiation, and a tiny amount of dark matter. As the universe expanded and cooled, small fluctuations in density led to the formation of the first structures, such as galaxies and clusters. The model posits that gravity, driven by both ordinary matter and dark matter, pulled these small density fluctuations together, forming larger cosmic structures over billions of years. One of the most compelling pieces of evidence supporting the LCDM model is the cosmic microwave background radiation, or CMB. This faint glow, which fills the universe, is thought to be the afterglow of the Big Bang, and its temperature fluctuations provide a snapshot of the early universe. These fluctuations align with predictions made by the LCDM model, showing that the distribution of matter in the universe today can be traced back to those early density variations. Moreover, the LCDM model explains the observed acceleration of the universe expansion, a phenomenon discovered in the late 1990s through observations of distant supernovae. This acceleration is attributed to dark energy, represented by lambda in the model. While the exact nature of dark energy remains one of the greatest mysteries in cosmology, the LCDM model successfully incorporates this component to explain why galaxies are moving away from each other at an accelerating rate. Additionally, the LCDM model accounts for the large-scale structure of the universe, including the distribution of galaxies and galaxy clusters. Simulations based on the model show how dark matter acts as a scaffolding for galaxy formation, with galaxies forming along the filaments of dark matter, creating a web-like structure throughout the universe. Observations of the distribution of galaxies in cosmic surveys match well with predictions from the LCDM model, reinforcing its validity. Furthermore, the model addresses the formation of various cosmic entities. Neutrinos, those elusive particles that are nearly massless and interact very weakly with matter, play an intriguing role in the study of dark matter and dark energy. Even though they are not considered dark matter themselves, scientists are keenly interested in neutrinos because they can provide insights into the fundamental workings of the universe. Dark matter, which makes up about 27% of the universe, and dark energy, accounting for about 68%, remain largely mysterious. Yet neutrinos can help scientists unravel some of these mysteries. For instance, researchers study neutrinos produced in high-energy processes, such as supernovae or cosmic rays, to gain a better understanding of the conditions that may have also contributed to the formation of dark matter. These neutrinos can carry information about the early universe, and their properties can shed light on how matter and energy behave at cosmic scales. Moreover, neutrinos are produced in great quantities in the Sun, where they are created through nuclear fusion, and studying them allows scientists to probe the core processes of stars, which may relate to the larger cosmic picture, involving dark energy and dark matter. Additionally, experiments designed to detect these tiny particles, like those conducted in deep underground labs or large observatories, help scientists refine their models of particle physics, which can influence our understanding of the universe's expansion driven by dark energy. Interestingly, the interactions of neutrinos with other particles can also lead to observable effects in cosmic structures, helping astrophysicists understand the distribution of dark matter across galaxies. In this context, the behavior of neutrinos could potentially reveal clues about their interactions with dark matter, suggesting that there might be more connections than initially thought between these seemingly distinct phenomena. As scientists continue to explore the universe's fabric, the study of neutrinos not only enhances our knowledge of the particles themselves, but also enriches our understanding of the cosmos, illuminating the pathways through which dark matter and dark energy influence the universe's evolution. Thus, while neutrinos are not dark matter themselves, their study is crucial in piecing together the larger puzzle of the universe, providing a unique perspective into the forces that shape it. Gravitational waves, which are ripples in spacetime caused by some of the most violent and energetic processes in the universe, such as merging black holes or neutron stars, have opened a new window into understanding the cosmos. And, intriguingly, they can also provide insights into the elusive nature of dark matter. Dark matter, which makes up about 27% of the universe, interacts with regular matter through gravity, but does not emit, absorb, or reflect light, making it invisible and challenging to detect directly. When scientists detected gravitational waves for the first time in 2015, it was a groundbreaking achievement that confirmed a key prediction of Albert Einstein's general theory of relativity, but it also sparked curiosity about how these waves could help unravel the mysteries surrounding dark matter. One interesting avenue of research involves the effects of dark matter on the formation and behavior of astrophysical objects that produce gravitational waves. For instance, if dark matter has a substantial influence on the dynamics of galaxies, this could affect how binary systems of stars or black holes form and evolve. If researchers can better understand the population and distribution of these binaries, it might provide clues about the nature of dark matter itself. Additionally, scientists are investigating whether gravitational waves can reveal information about the structure of dark matter, particularly in regions where it is dense, such as in the centers of galaxies. The way gravitational waves propagate through different environments could be influenced by the presence of dark matter, and analyzing their signals might help identify how dark matter is distributed in the universe. Moreover, there are theoretical models that suggest dark matter could consist of lightweight particles, known as fuzzy dark matter, which would behave differently under certain conditions. If such particles exist, they might create a distinct gravitational signature that could be detectable through gravitational waves. Researchers are exploring the potential for future gravitational wave observatories, like the proposed space-based LISA, to capture signals that could indirectly provide evidence for these exotic forms of dark matter. In summary, while gravitational waves primarily serve as a tool for understanding massive cosmic events, they also hold the potential to shed light on the mysterious dark matter that pervades the universe. By studying the interactions between gravitational waves and the structures influenced by dark matter, scientists can glean new insights into one of the biggest questions in modern astrophysics. As gravitational wave astronomy continues to advance, it may offer a novel way to probe the fundamental components of our universe, including the elusive dark matter that remains one of its greatest mysteries. Studying dark matter presents a range of observational challenges that scientists continue to grapple with, primarily because dark matter does not emit, absorb, or reflect light, making it invisible to our current telescopes, which rely on electromagnetic radiation to observe celestial objects. This means that, unlike stars or galaxies, dark matter cannot be seen directly, leading researchers to infer its presence through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. For instance, when astronomers observe the rotation curves of galaxies, they notice that the outer regions of galaxies rotate at much higher speeds than expected based on the visible mass alone, suggesting there is unseen mass, or dark matter, present. Furthermore, the challenge intensifies due to the fact that dark matter is thought to account for about 27% of the universe's total mass-energy content, yet its exact nature remains unknown. Scientists have proposed various candidates for dark matter particles, including weakly interacting massive particles, or WIMPs, and axions, but none have been conclusively detected so far. The elusive nature of dark matter leads to significant difficulties in designing experiments, detectors, and observational techniques that can successfully identify and study these hypothetical particles. Another observational challenge is related to the scale at which dark matter operates. Dark matter's effects are most noticeable at large scales, such as clusters of galaxies, rather than at smaller, more easily observable scales. This means that, while we can see the effects of dark matter through gravitational lensing where light from distant objects is bent by the mass of dark matter, we still have to deal with the complexities of interpreting these observations accurately. Additionally, the presence of other astrophysical phenomena, such as normal matter or radiation, can complicate the analysis and lead to potential misinterpretations of the data. Moreover, the distribution of dark matter in the universe is not uniform. It tends to clump together in certain areas, forming halos around galaxies. Observing these halos and understanding their structure and dynamics requires sophisticated simulations and models, further complicating the observational landscape. The potential for systematic errors in these models means that interpreting data from observations can lead to different conclusions about the properties and behavior of dark matter. Finally, there is the issue of cosmic variance, which refers to the statistical uncertainty in measurements due to the limited number of observed structures in the universe. Since dark matter is believed to influence the formation of galaxies and clusters, studying a small sample can lead to inaccurate generalizations about its properties. Baryonic acoustic oscillations, often abbreviated as BAOs, are essentially regular, periodic fluctuations in the density of visible matter, which include baryons, in the universe. These oscillations originated shortly after the Big Bang, during a time when the universe was filled with hot plasma. As the universe expanded and cooled, sound waves propagated through this plasma, creating pressure waves that led to the formation of regions of higher and lower density. These regions eventually influenced the large-scale structure of the universe, leading to the galaxies and clusters we observe today. The key insight that BAOs provide into dark energy lies in their role as a cosmic ruler, helping astronomers measure the expansion of the universe. When we look at the distribution of galaxies, we can identify patterns that correspond to these acoustic oscillations. By mapping the distances between galaxies, researchers can determine how the universe has expanded over time. The presence of baryonic acoustic oscillations serves as a standard ruler because the scale of these oscillations is well understood, allowing scientists to measure distances in the universe with great precision. As the universe expands, the effects of dark energy, which is thought to drive this acceleration, become apparent. By analyzing the distribution of galaxies and the signature of BAOs within it, scientists can infer how the expansion rate of the universe has changed over time, shedding light on the nature of dark energy. Dark energy is a mysterious force that appears to be responsible for the accelerated expansion of the universe, and understanding it is one of the biggest challenges in modern cosmology. The relationship between baryonic acoustic oscillations and dark energy can be observed through the varying expansion rates at different epochs of the universe. When scientists measure the BAO scale and compare it to the rate of expansion, they can derive important parameters about dark energy, such as its equation of state. This equation describes how dark energy behaves over time and whether it changes as the universe evolves. In this context, baryonic acoustic oscillations act like a cosmic background noise, a fixed pattern that helps astronomers make sense of the larger, more chaotic universe. By observing the BAO signature in the cosmic microwave background radiation, as well as in the distribution of galaxies, researchers can create a detailed picture of how the universe's expansion has changed, providing crucial insights into the properties of dark energy. This interplay between BAOs and dark energy not only helps refine models of the universe's expansion, but also guides theorists in understanding the fundamental forces at play in the cosmos, revealing how warm dark matter is a fascinating concept in astrophysics, which refers to a type of dark matter that has a mass and velocity between that of cold dark matter and hot dark matter. To understand this better, we need to look at the different categories of dark matter. Cold dark matter, often abbreviated as CDM, is composed of particles that move slowly compared to the speed of light, which allows them to clump together and form the large-scale structures we observe in the universe today, like galaxies and galaxy clusters. On the other hand, hot dark matter consists of lighter particles, such as neutrinos, which travel at speeds close to that of light, and this rapid movement prevents them from clustering effectively, leading to a smoother distribution in the cosmos. Warm dark matter, therefore, occupies a middle ground, consisting of particles that are more massive than neutrinos, but lighter than the particles that make up cold dark matter. A commonly suggested candidate for warm dark matter is the sterile neutrino, a hypothetical type of neutrino that does not interact through the usual weak force, making it difficult to detect. The key difference between warm dark matter and its colder counterpart lies in their effects on the formation of cosmic structures. Because warm dark matter particles have more thermal energy than cold dark matter particles, they can move more freely and do not clump together as efficiently in the early universe. This leads to a different distribution of matter, which could potentially resolve some discrepancies in galaxy formation theories, particularly at smaller scales. For instance, in models that include warm dark matter, we might expect to see fewer small galaxies than what is predicted by cold dark matter models. This is because warm dark matter's ability to smooth out fluctuations in density means that the small-scale structure formation is suppressed compared to what cold dark matter would allow. Consequently, galaxies would be more massive, and there would be fewer dwarf galaxies scattered across the universe. The exploration of warm dark matter has gained interest as researchers look to explain certain observations that do not perfectly align with predictions made by the cold dark matter paradigm. In recent years, scientists have been conducting simulations and observational studies to examine the implications of warm dark matter on the universe's evolution, with hopes of gaining insights into dark matter's true nature. As we continue to delve into the mysteries of dark matter, the distinction between warm and cold dark matter, along with their respective roles in cosmic structure formation, remains a critical area of inquiry, helping us piece together the complex puzzle of our universe's history. And the existence of dark matter plays a crucial role in shaping our understanding of the cosmic baryon budget, which refers to the distribution of ordinary matter, or baryonic matter, in the universe. Baryonic matter includes elements like hydrogen, helium, and heavier elements that make up stars, galaxies, and planets, while dark matter, though invisible and not directly detectable, makes up a significant portion of the universe's total mass, influencing how baryonic matter behaves and clusters. Observations suggest that dark matter contributes about 27% of the total energy density of the universe, compared to the roughly 5% that baryonic matter represents. This ratio is vital because it indicates that dark matter is the dominant component when it comes to gravitational effects in large-scale structures, such as galaxy clusters. When we observe the cosmic microwave background radiation, which is the afterglow of the Big Bang, we can see how baryons and dark matter interact. The presence of dark matter helps explain the temperature fluctuations in this radiation, revealing how matter clumps together under gravitational influence. This clumping is essential for the formation of galaxies, as dark matter forms a sort of cosmic scaffold, allowing baryonic matter to accumulate and form stars and galaxies. Without dark matter, the universe would look vastly different, with galaxies unable to form or maintain their structure. Furthermore, the cosmic baryon budget is also affected by processes such as cosmic reionization, where the first stars emitted enough energy to ionize surrounding hydrogen gas. Dark matter's gravitational pull helps retain this baryonic matter in galaxies, ensuring that they can hold on to their gas and dust, which are necessary for star formation. Additionally, studies of galaxy formation and evolution have shown that the amount of baryonic matter that can be formed is closely tied to the amount of dark matter present in a given region. In regions of high dark matter density, we see an abundance of baryonic matter, indicating that dark matter not only influences the amount of visible matter, but also its distribution across the universe. Moreover, the baryon fraction, which is the proportion of baryonic matter relative to total matter, gives us insights into how much of the universe's mass is accounted for by ordinary matter versus dark matter. Researchers have found that in clusters of galaxies, the baryon fraction is lower than expected if only baryonic matter were involved. This discrepancy suggests that a significant amount of baryonic matter is not in the form we typically observe, like stars and gas, but instead is in the dark energy, a mysterious force that makes up about 68% of the universe, is thought to be responsible for the accelerated expansion of the cosmos. This phenomenon raises intriguing questions about the nature of the universe and its possible extensions, particularly regarding the concept of the multiverse. The multiverse theory suggests that our universe is only one of many, possibly infinite, universes that exist simultaneously, each with its own unique properties, laws of physics, and dimensions. The implications of dark energy for this concept are profound and, at times, quite complex. First, dark energy influences the rate at which our universe expands, which could have significant consequences for how other universes might behave. If dark energy continues to drive the accelerated expansion indefinitely, it could lead to a scenario known as the Big Freeze, where galaxies move so far apart that they eventually become unobservable, isolating each universe from one another. This would mean that while our universe is expanding, it could also suggest that other universes might be doing the same, each following its own path, determined by its unique properties of dark energy. Furthermore, the presence of dark energy could imply that different universes in the multiverse might have varying amounts of this force, leading to different cosmic fates. Some universes might experience rapid expansion, while others could have a more stable, slower expansion, or even collapse under the weight of gravity. This leads to fascinating considerations about the conditions necessary for life, as the characteristics of dark energy could play a crucial role in the development of galaxies, stars, and planets within each universe. If dark energy varies, then the potential for life, as we understand it, could also vary drastically from one universe to another. Moreover, the very nature of dark energy could suggest that our universe is part of a larger, interconnected multiverse structure. For instance, theories such as string theory and quantum mechanics hint at the existence of multiple dimensions beyond the three we experience daily, and dark energy might be a key to unlocking the mysteries of these dimensions. If dark energy is tied to extra dimensions, it may indicate that our universe's expansion is influenced by interactions with other universes, allowing energy or matter to flow between them in ways that we have yet to comprehend. Additionally, the cosmological constant, a key component of dark energy, is an important factor in understanding the stability of a multiverse. If the constant is truly constant across different universes, it could mean that the laws of physics are uniform throughout the dark matter plays a crucial role in the formation and development of galaxy clusters, acting as an unseen scaffolding that influences how visible matter interacts and clusters together. To understand this, it's important to recognize that dark matter, which makes up about 27% of the universe, does not emit or absorb light, making it invisible to telescopes. However, it does exert gravitational forces that can be detected through its effects on visible matter, radiation, and the large-scale structure of the universe. When the universe began to expand after the Big Bang, small fluctuations in density began to form in both dark matter and normal matter. Over time, these fluctuations in dark matter density created gravitational wells, which attracted regular matter, such as gas and stars, leading to the formation of galaxies. As galaxies began to emerge, dark matter continued to play a pivotal role in their evolution. It acts as a gravitational glue that holds the galaxies together, allowing them to merge and form larger structures known as galaxy clusters. In these clusters, the dark matter halo surrounds the visible galaxies, creating a region of high mass density that influences how galaxies move and interact. The presence of dark matter in these clusters is inferred through observations of gravitational lensing, a phenomenon where light from distant objects, like galaxies, is warped by the gravity of the cluster, allowing astronomers to map the distribution of dark matter. Moreover, the distribution of dark matter within galaxy clusters is not uniform. It tends to be more concentrated toward the center, where the gravitational pull is strongest. This concentration of dark matter impacts the way galaxies within the cluster behave, including their velocities and trajectories. Studies show that galaxies in clusters move faster than those in isolation, a result of the gravitational influence of the surrounding dark matter. This effect is crucial in understanding not just the formation of galaxy clusters, but also their long-term evolution and fate in the cosmos. In addition, the interaction between dark matter and baryonic matter, which includes gas that can cool and form stars, is essential for the growth of structures in the universe. As dark matter halos grow, they can compress the surrounding gas, triggering star formation and leading to the creation of new galaxies within the clusters. This interplay between dark matter and baryonic matter shapes the characteristics of galaxy clusters, influencing their size, mass, and the number of galaxies they contain. Research into dark matter continues to be a hot topic in astrophysics, as scientists seek to uncover its true nature and understand its role in the cosmos. Experiments. Dark energy plays a crucial role in the mysterious acceleration of the universe's expansion. To understand this, after the Big Bang, the universe began to expand rapidly, but for a long time, this expansion was slowing down due to the gravitational pull of matter, both visible and dark. Scientists once thought that the expansion would eventually halt and possibly reverse, collapsing back into a big crunch. However, observations in the late 1990s, particularly from distant supernovae, revealed something unexpected. The rate of expansion was not slowing down, but rather speeding up. This startling discovery led to the concept of dark energy, which is thought to make up about 68% of the universe. While we can't see dark energy directly, its effects can be observed through its influence on cosmic structures and the rate of expansion. One of the leading theories suggests that dark energy is a constant energy density that fills space uniformly, exerting a negative pressure that drives galaxies apart. This behavior contrasts sharply with gravity, which pulls matter together. Researchers propose several models to explain dark energy, with the most popular one being the cosmological constant, introduced by Albert Einstein in his equations of general relativity. In this model, dark energy is a fixed energy density that remains constant over time. Other theories suggest that dark energy could vary over time or be related to a field that changes throughout the universe. One fascinating aspect of dark energy is how it relates to the fate of the universe. As space continues to expand, dark energy's influence grows, potentially leading to scenarios such as the Big Freeze, where galaxies drift apart beyond the observable horizon, leaving a dark, cold universe in the distant future. Scientists continue to study dark energy through various means, including observing cosmic microwave background radiation, galaxy distributions, and gravitational lensing to gather more insights into its properties and implications for the universe. This ongoing research not only deepens our understanding of dark energy, but also raises fundamental questions about the nature of space, time, and the very fabric of reality itself, inviting both curiosity and wonder about the cosmos around us. Large-scale structure surveys, which map the distribution of galaxies and other cosmic structures across vast regions of the universe, play a crucial role in enhancing our understanding of dark matter, a mysterious substance that makes up about 27% of the universe's total mass energy content. By observing how galaxies are clustered together and how they move, scientists can infer the presence and influence of dark matter, even though it does not emit light or interact with electromagnetic forces in ways that we can directly observe. These surveys use advanced telescopes and sophisticated imaging techniques to gather data on billions of galaxies, allowing researchers to create three-dimensional maps of the universe. One of the key insights from these surveys is that the distribution of visible matter, like stars and galaxies, follows a pattern that is heavily influenced by the underlying dark matter. Dark matter acts as a gravitational glue, pulling galaxies together and shaping the large-scale structure we see today. For instance, when scientists study galaxy clusters, they find that the mass of these clusters, as inferred from their gravitational effects on surrounding galaxies and light, often exceeds the mass we can see in ordinary matter. This discrepancy reveals the presence of dark matter, which, while invisible, exerts gravitational forces that can be measured. In addition to mapping the current state of cosmic structures, large-scale structure surveys also help us understand how these structures evolved over time. By observing distant galaxies, we can see them as they were billions of years ago, showing us how dark matter has influenced their formation and growth. This temporal perspective allows astronomers to test models of structure formation which predict how dark matter should behave in different scenarios. Moreover, the cosmic microwave background radiation, which is the afterglow of the Big Bang, serves as another source of information about dark matter, and large-scale structure surveys complement this data. By correlating observations from the cosmic microwave background with galaxy distribution, researchers can refine their models of dark matter and its properties, enhancing our understanding of its role in cosmic evolution. Additionally, these surveys have led to the discovery of phenomena like gravitational lensing, where the light from distant galaxies is bent around massive galaxy clusters due to dark matter's gravitational field. This effect not only reveals the presence of dark matter, but also allows scientists to map its distribution with greater precision, providing further insights into its nature and behavior. Through these various methods, large-scale structure surveys continue to shed light on dark matter, helping scientists unravel one of the universe's most profound mysteries, while also paving, in the realm of astrophysics, the quest to understand dark matter has spurred a plethora of technological advancements that significantly enhance research in this enigmatic field. One of the most notable advancements is the development of highly sensitive detectors, such as liquid argon and germanium-based detectors, which are designed to capture the faintest interactions that dark matter particles might have with normal matter. These detectors, often placed deep underground to shield them from cosmic rays and other background noise, operate at incredibly low temperatures, allowing them to pick up minuscule energy changes from potential dark matter collisions. Moreover, advancements in computational power and algorithms have revolutionized data analysis in dark matter research. With the ability to process vast amounts of data collected from particle accelerators, telescopes, and observatories, scientists can now run complex simulations that model the behavior of dark matter in different cosmological scenarios. This computational prowess enables researchers to refine their hypotheses and test them against observational data more effectively than ever before, leading to a deeper understanding of how dark matter interacts with the universe. In addition, the rise of large-scale astronomical surveys, such as the Vera-C, Rubin Observatory's legacy survey of space and time, has equipped scientists with unprecedented data about the distribution of galaxies and gravitational effects across the cosmos. These surveys utilize advanced imaging technology and sophisticated software to map the universe in great detail, revealing patterns that suggest the presence of dark matter, even though it cannot be observed directly. Another significant advancement is the emergence of particle colliders, like the Large Hadron Collider, which allows physicists to create conditions similar to those just after the Big Bang. Here, researchers conduct experiments that could potentially produce dark matter particles, enabling direct detection and study of their properties. These experiments rely on cutting-edge technology, including superconducting magnets and high-speed data acquisition systems, to manage the extreme conditions and vast amounts of data generated during collisions. Additionally, gravitational wave astronomy has opened a new window into dark matter research. Instruments like LIGO and Virgo detect ripples in space-time caused by massive astronomical events, and the data they provide can help scientists understand how dark matter affects the formation and evolution of galaxies. By analyzing these gravitational waves, researchers can infer the presence of dark matter in regions of space where traditional observations may not be effective. Furthermore, the development of dark matter simulations, which utilize artificial intelligence and machine learning, represents a cutting-edge approach to exploring the complexities of dark matter. These technologies can analyze large data sets from various sources, identifying patterns, observations of the large-scale structure of the universe, which include the distribution of galaxies, galaxy clusters, and cosmic filaments, play a crucial role in understanding dark energy, a mysterious force that drives the accelerated expansion of the universe. As scientists study the large-scale structure, they notice patterns and distributions that reveal how matter is clumping together under the influence of gravity, while also showing how the expansion rate is influenced by dark energy. One significant way these observations constrain dark energy models is through the measurement of cosmic microwave background radiation, which provides a snapshot of the early universe, allowing researchers to understand how matter and energy have evolved over billions of years. By mapping the cosmic web, scientists can observe how gravitational interactions affect the growth of structures over time, leading to insights about the density and behavior of dark energy. Furthermore, the way galaxies are distributed across vast distances reveals much about the effects of dark energy. If dark energy were to behave differently than the current models predict, the distribution of galaxies would show noticeable deviations from the observed patterns. For instance, if dark energy were repulsive, structures would be more spread out than we see today. Conversely, if dark energy were weaker than anticipated, we would expect more clumping of galaxies. Advanced surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, have provided extensive data on galaxy positions and movements, allowing astronomers to create detailed maps of the universe that can be compared against dark energy models. Additionally, gravitational lensing, a phenomenon where massive objects bend light from more distant galaxies, offers another way to test these models. The degree of bending can inform scientists about both the amount of matter and the influence of dark energy in a given region of space. If the observations of lensing do not match predictions made by dark energy models, it suggests that our understanding of dark energy needs to be refined. Moreover, the growth of large-scale structures can be quantified using simulations of the universe, which incorporate various dark energy models. By comparing these simulations with actual observations, researchers can determine which models are consistent with the data, effectively narrowing down the possibilities. In essence, the large-scale structure of the universe acts as a cosmic laboratory, where the interplay between gravity and dark energy can be studied, leading to better constraints on the properties and behavior of dark energy. By analyzing the cosmos at different scales, across vast distances and epochs, scientists continue to refine their understanding, seeking to unravel one of the greatest mysteries of modern cosmology, which ultimately impacts the bullet cluster. A fascinating astronomical phenomenon, is significant in the study of dark matter for several reasons. Its discovery has provided crucial evidence for the existence of this elusive substance. The bullet cluster consists of two colliding galaxy clusters, which, when observed, reveal intriguing insights into the nature of dark matter. When these two clusters collided, the hot gas within them interacted, creating a brilliant display of X-ray emissions, while the majority of the mass, believed to be dark matter, passed through the collision without much interaction. This separation of visible mass and gravitational mass is key to understanding dark matter, as it suggests that most of the mass in the universe is not in the form of ordinary matter, which emits light, but instead is composed of this unseen material. The significance becomes even clearer when we consider how scientists measured the gravitational lensing effects caused by the bullet cluster. Gravitational lensing occurs when massive objects bend the light from objects behind them, allowing researchers to map the distribution of mass in the clusters. By analyzing this lensing effect, scientists identified that the majority of the mass in the bullet cluster is located in regions that do not correspond to the visible matter, indicating a substantial presence of dark matter. This observation supports the hypothesis that dark matter does not interact with electromagnetic forces, which means it neither absorbs nor emits light, making it invisible and detectable only through its gravitational effects. Furthermore, the bullet cluster provides a natural laboratory for testing various theories about dark matter. For instance, the collision events challenge modifications to gravity theories, like Mond-modified Newtonian dynamics, which attempt to explain the observed phenomena without invoking dark matter. The behavior of the bullet cluster, particularly the way the dark matter and baryonic matter, ordinary matter, are distributed after the collision, strongly favors the existence of dark matter as a separate entity, rather than a modification of existing physics. In addition to its role in supporting dark matter theories, the bullet cluster also raises intriguing questions about the formation and evolution of galaxy clusters. The dynamics of such collisions can provide insights into how clusters grow over time and how dark matter influences the cosmic structure. The study of the bullet cluster has paved the way for more advanced simulations and models that aim to explain the large-scale structure of the universe, enhancing our understanding of cosmic evolution. Overall, the Bullet Cluster stands as a cornerstone in the field of cosmology, illustrating the importance of observational evidence in understanding dark matter, while simultaneously inspiring further research into the fundamental components of our universe. Dark matter, a mysterious and invisible substance that makes up about 27% of the universe, plays a significant role in our understanding of cosmic inflation theories. Cosmic inflation refers to the rapid expansion of the universe that is believed to have occurred just after the Big Bang. And while we often think of visible matter and radiation during this period, dark matter's influence is profound and essential. Inflationary theories suggest that, during the first moments of the universe, it expanded exponentially, smoothing out any irregularities and creating a uniform cosmos. Dark matter, with its gravitational effects, helps to shape the structure of the universe we see today, influencing how galaxies and galaxy clusters form and evolve. In the context of inflation, dark matter can affect the dynamics of this rapid expansion. Theories posit that dark matter can contribute to the energy density of the universe, which is crucial for understanding the forces at play during inflation. Some models suggest that dark matter might interact with inflaton field hypothetical fields that drive inflation, thereby influencing the nature and rate of inflation. For instance, if dark matter has certain properties, such as a non-negligible mass or specific interactions, it could alter the expansion rate, leading to different predictions about the universe's large-scale structure. Moreover, the existence of dark matter can help explain some of the observed patterns in the cosmic microwave background radiation. The fluctuations in this radiation provide a snapshot of the universe when it was just 380,000 years old, and dark matter's gravitational pull could have influenced these patterns, hinting at its role during the inflationary period. Researchers also investigate how dark matter's clustering behavior, occurring after inflation, could leave imprints on the structure of the universe, subsequently affecting how galaxies form and the distribution of cosmic structures. Additionally, dark matter could play a role in the so-called post-inflationary phase, where its influence could provide insights into the transition from inflation to the more stable state of the universe we observe today. Some theories postulate that the interactions between dark matter and other forms of energy could lead to a gradual slowing down of inflation, helping to bridge the gap between the rapid expansion and the slower, more structured universe that followed. Understanding dark matter's influence on cosmic inflation not only enhances our grasp of the universe's early moments, but also helps cosmologists refine their models, leading to predictions that can be tested against observations. As researchers continue to gather data from telescopes, scientists are constantly seeking to unravel the mysteries of dark matter and dark energy, which together make up about 95% of the universe, yet remain largely unknown. One of the most significant future experiments aimed at investigating dark matter is the Long Baseline Neutrino Facility, or LBNF, which will be located at Fermilab in the United States. This facility is designed to study neutrinos, elusive particles that could shed light on dark matter interactions. It will send neutrinos on a long journey to a detector located over 1,000 kilometers away, allowing scientists to observe how these particles behave and potentially revealing connections to dark matter phenomena. In addition to LBNF, the European Space Agency is planning the Euclid mission, which is set to launch in 2023. This satellite will focus on mapping the geometry of the dark universe, aiming to understand the role of dark energy in shaping the universe's structure. By observing distant galaxies, Euclid will measure their distances and the rate at which the universe is expanding. This data could help answer fundamental questions about the nature of dark energy, which is thought to be responsible for the accelerated expansion of the universe. Meanwhile, the Large Hadron Collider LHC continues its groundbreaking work at CERN, with plans for the High Luminosity LHC, which aims to increase the collision rate of particles. This upgrade, expected to be completed in the late 2020s, will allow physicists to collect more data and search for possible candidates for dark matter. One of the theories involves supersymmetry, which predicts the existence of new particles that could be dark matter candidates, and the LHC's enhanced capabilities may provide critical insights into their existence. Another exciting endeavor is the proposed NASA mission called the Wide Field Infrared Survey Telescope, or WFIRST, which will survey the skies in infrared light. Scheduled for launch in the mid-2020s, WFIRST will help to understand dark energy by observing the distribution of galaxies and the expansion of the universe over time. By studying how galaxies cluster and how light from distant objects is affected by gravitational lensing, scientists hope to gain a clearer picture of how dark energy influences cosmic structures. Additionally, several underground experiments, such as the Deep Underground Neutrino Experiment DUNE, are set to explore dark matter through direct detection techniques. DUNE will be designed to search for rare interactions between dark matter and normal matter, using a massive detector located deep underground to shield it from cosmic